energy was actually lost during this collision. Let's look at it in terms of the inelasticity of this problem. And we've done this before, so we should be getting used to this idea. The initial kinetic energy before the bullet hits the block is going to be 1/2 little m times v naught squared. It would be 1/2 times 10 to the minus 3 kilograms times 10 to the 3 meters per second squared. So that would be 500 joules. Okay, so here's 1,000. Here's 1,000 times bigger, right? But then you square it, so it's 1,000,000 divided by 1,000 is 1,000 times 1/2 is 500. Then KE final is going to be 1/2 times little m plus big M times v squared. So that would be 1/2 times, essentially 1.001 kilograms times 1 meter per second squared. So that essentially is 0.5 joules. Okay, so look at that. We started out with 500 joules, and now during the swing we've only got 0.5. So that's 1/1000th of the original energy. And so that means that 999 parts out of 1,000 has been lost during the collision. So we can say then that the percent energy lost is delta KE divided by KE naught. Okay, so the change in kinetic energy then is 499.5. It's 500 minus 0.5 divided by the original kinetic energy is 500 times 100. And so that gives us 99.9%. Okay, so that's the percent energy lost. And another way of saying that is just 0.1% of the energy remains after the collision. And so much of the energy has been lost, you would think that we wouldn't even have a problem anymore. But by using conservation of momentum and staying consistent with it, we can solve a problem like this, which would, without the principles of momentum conservation, be a much more challenging problem to solve.